The advent of X-ray telescopes have allowed us to detect millions of X-ray sources in our universe. Now, one of the very first ones that was detected was Cygnus X1. And this very quickly became a candidate for being a black hole because the X-rays that were being emitted from this object were changing every 100th of a second. So let's start off with a simple model of Cygnus X1 as a black hole with a disk of spiralling, infalling matter. Now, just like water going down a plug hole, the closer the matter gets to the black hole, the faster it moves. And the faster it moves, the hotter it gets and the more X-rays it will emit. Now, if different regions of this disk were emitting X-rays in different ways, then we would measure just an average X-ray brightness. But the fact that the X-rays we observe from Cygnus X1 are changing, that tells us that the whole disk is changing together. And this sets a maximum upper limit on the size of this object. And we can work that out from the distance, which is going to be the speed of light times the time with which this disk is changing. Now, the speed of light is just 3 times 10 to the 8 meters per second. And we know that the X-rays are changing every 100th of a second. So you can put that together, and that gives you a distance of 3,000 kilometres, which is roughly the distance between Edinburgh and Moscow, or if you're in the US, the distance between New York and Seattle. If we point an optical telescope towards Cygnus X1, then we find that there's a massive blue supergiant star really close to the X-ray source. And careful monitoring of this star shows that it's orbiting an invisible friend every 6 days. How do we know that? Well, imagine you're standing on the side of a Grand Prix racecourse and you've got your eyes closed and a car goes past you. I bet you can tell me which way it went. Now, that effect has got a grand name called the Doppler effect, and we can use it to tell us whether things are moving towards us or away from us. And if we monitor this massive blue supergiant star, we can see that it comes towards us for 3 days and then away from us for 3 days. And so it's orbiting something every 6 days. Now, in physics, we like to start a problem by looking at the simplest model. So let's take our black hole, Cygnus X1, and our blue supergiant that's orbiting it. But let's assume that the mass of our supergiant is much smaller than our black hole, and then we can assume that it orbits in a perfect circle. Now, our black hole mass, we'll say that's a mass capital M, and our blue supergiant, we'll say that's got a mass little m. Now, we've measured the velocity of the blue supergiant. We know that it's moving with a speed v, and there's going to be some separation between these two objects, radius r. Now, the velocity that we measure with the Doppler shift is just going to be 2 pi r, the distance that the supergiant travels in one orbit, divided by the time that it takes to go around that orbit. And we know that it orbits every 6 days. Now, what's keeping these two objects bound together? Well, it's gravity. And there's an equation for the force of gravity, and that is Newton's gravitational constant times the mass of the two objects divided by their separation squared. Now, our blue supergiant is orbiting round and round, so it has a centripetal force, and the equation for that is given by its mass times its velocity squared over the radius. Now, it's the gravitational force that's sourcing this centripetal force, so I can equate these two things. and then I can just do some algebra to tidy those equations up. Now, it's the mass that I want to find out because I'm trying to find evidence that this is a black hole. I've measured the velocity using the Doppler effect, but I don't know this radius. I don't know the separation between these two objects. However, I do have some information here. So I can rearrange this equation. That the separation between these two objects is just the velocity times the time over 2 pi. And I can put that equation back into here and rearrange things, and I'll leave that as an exercise for you. We'll find the mass of the black hole. It's just the velocity cubed times the time over 2 pi g. So just by using the physics of gravity and observations of the speed with which the blue supergiant is moving and the time that it takes to orbit its invisible black hole friend, I can calculate a mass for our black hole. Now, what I've shown you there is how we can use gravity to measure mass. And unfortunately, in the case of Cygnus X1, it's not quite as simple as the physics I outlined there, because the massive blue supergiant star is actually more massive than the black hole that it's orbiting. But at least gives you an idea of how we can measure masses in the universe. If you do the calculation correctly, taking into account the mass of the supergiant star as well, we find out that the black hole Cygnus X1 is about 16 times the mass of our own sun. Now let's put that fact together with the size of the object that we discovered earlier, which was 3,000 kilometres. Put those two things together, 16 times the mass of the sun within 3,000 kilometres, you've got a very, very dense object there. Now, this isn't proof that it's a black hole, but it's very strong evidence supporting that theory. And to be honest, we're never going to know whether Cygnus X1 really is a black hole or not, but it's the best evidence that we've got. Today we focused on a single black hole, Cygnus X1, but the X-ray technology can be used to map out black holes in our whole universe, including the supermassive black holes that exist at the centre of each and every galaxy. Recently, astronomers have discovered that there's a secret relationship between the black hole and its galaxy, with the most massive galaxies hosting the most massive beasts at their core. If it wasn't for X-ray telescope technology, we wouldn't have discovered these amazing black holes, the stuff of science fiction shown to be reality.